In this video, we'll be looking at the first section of the field theory topic, focused on gravitational field strength. Now, when dealing with gravity, we are dealing with an invisible force field, a field that causes force-based effects on objects of the relevant property. So for gravitational fields, we're talking about an attractive force that affects objects with mass. Now, we know that there is no significant effect to gravity on objects unless there is an exceptional difference between the masses of those two objects. So two people will not have a massive effect gravitationally on each other because they are of similar mass. But the Earth is significantly greater mass than a person. So we feel that effect due to the massive difference. So the region around the mass is where the field is known to be. Where previously looking at gravitational fields, we considered it to be 9.81 newtons per kilogram as a uniform field across the Earth. Now, this is only really true if we look very closely near the surface of the Earth, where we can treat the field as being uniform. So this is not the real case, but as far as we deal with gravity on the surface of the Earth, it might as well be considered uniform. So this allows us to keep a constant value, as we previously have, for gravity, and it will generally be correct for anything we deal with in everyday life. So we can form the basic equation for this, where G is equal to F over M. So F is our force, the effect of gravity, so weight essentially, and that's measured in newtons. M is our mass, our point mass, whatever the object is, in kilograms, and G is the gravitational field strength. Now we know we consider this to be 9.81, or any other variant of that they give you in the exam. And we normally measure it, as we've said before, in newtons per kilogram. But it's worth reminding us of the link to something fairly straightforward with this, fairly basic, is acceleration gravity. Now previously in the mechanics topic, we've seen that acceleration due to gravity is going to be linked to the equation F equals ma. So we can see here that G, as we use it, is the same as acceleration. So as a result, we can easily say that the unit for gravitational field strength can also be considered to be meters per second squared. Now on the data sheet, both of these units are given, as you are given a value for G as gravitational field strength and acceleration due to gravity, both the same symbol of G. Now in reality, the further out you go, the less this uniform field concept will hold. Now we know gravity is an attractive force, but what we need to consider is where they're actually acting towards. So this pull is always towards the center of the mass. So we are treating the Earth as a point mass at the core. So if we consider this on a grand scale, we end up with radial lines, just as shown in this diagram. And they're all pointed towards that central point, the center of mass. Now, as the gravitational field is attractive, we need to show that with arrows pointing in towards, as though any mass placed in that field will follow those arrows. So the further away you move from the center of mass, you notice that the lines separate more and more and more, which means the force is weaker. As you approach the surface, they get closer together, resulting in a stronger field. So throughout all of this, we are treating the Earth as a point mass. This avoids any complexities of something being positioned inside the Earth or different densities at different positions due to different parts of the planet. we just treat it as a point mass, plain and simple. And we know that this idea of it weakening at distance follows what we've previously seen with the inverse square law, which is a critical thing to know and relate to in the entirety of this field's topic. So we can form our radial variant of the gravitational field strength equation here, where little g, our gravitational field strength, is equal to big G, big M, over r squared. So as we've said, little g is gravitational field strength in newtons per kilogram, or meters per second squared, whatever you choose. We then have two newer things to consider. So big M just represents the mass that is actually causing this gravitational field. So this, in this case, for the diagram, would be the Earth. So it's the origin of the gravitational field. R is the radius, as normal. But really what we're talking about is the distance from the center of this mass to the point we're considering. So if we want to know the gravitational field strength at a set point in orbit, for example, you'd have to measure from the center of the Earth. And big G is our new addition, the gravitational constant. This is a value that is provided on the equation sheet as with all other key constants, and it is given as the value 6.67 times 10 to the minus 11, with the most exciting unit that luckily you don't have to remember of newtons meters squared per kilogram squared. Now, sometimes you will be expected to illustrate this concept or be able to interpret a graph or select it in multiple choice. Luckily, the graph is fairly logical. It shows that the gravitational field strength rapidly decreases in strength as the radius, or radial displacement as it's shown here, increases. And this is simply following the inverse square law. It's pretty much what we would expect of this. So it's a very familiar graph for any inverse square law effect. Thank you for your time.